right? Today we're very happy to have our own Sujay to tell us about inverse Hamiltonian reduction for W-algebras in type A.
Thank you, Ron. I'm really delighted to be here. As a warning, I just recovered from COVID, so I might not be at my 100%. So if I'm not able to answer your question, that's definitely why. But yeah, so I'll explain all these words on the board as I go along. But for now, to just give a brief outline, to give you like the whole schematic approach of what's going to happen, for every nilpotent orbit in type A, so that's mu sitting inside the null cone of GLN, again, one can associate a certain kind of, well, there are two things. You can associate a kind of associative algebra or a vertex algebra, both of which are called W-algebras, called W mu, where mu is the label of the nilpotent orbit I'm associating this to. And at its most concrete and perhaps least useful, inverse Hamiltonian reduction refers to a sort of like series of embeddings amongst these W-algebras. So the whole conjecture of inverse Hamiltonian reduction says that I should have these embeddings of associative or vertex algebras between W mu embedding into W mu prime, tensor some auxiliary algebra, which should look like the localization of differential operators on C, say, to some multiplicity. And this should happen whenever O mu prime, so whenever O mu, so that's the guy on the left, the nilpotent orbit is contained in the closure of the nilpotent orbit on the right. So in terms of the dominance ordering of partitions, whenever mu prime is a bigger partition than mu, I should have this like embedding.
Where does this conjecture come from?
So it comes all the way, like the first sort of example of this is all the way back in like the 1990s. There was a conjecture of Semi-Kantov from a paper called Inverting the Hamiltonian Reduction in String Theory. That's also where the name comes from, where he does this for the very explicit example of SL2 with the Vertex algebra. He just like does this by hand. He writes down this embedding and notices that this exists and might extend. As to
The one with the characters and that's in trouble, there's characters there.
yeah, so for SL2, we would have, this would be W11 includes into W20 times just differential operators on C star. That's my localization. That was like the original.
And the first guy has two copies of the Boden.
This guy?
Yeah.
This guy's just SL2. This is just the current algebra SL2. So the claim here is that the current algebra of SL2 includes into the Vertex algebra times something that looks like, well, differential. So in the vertex algebra setting, this would be chiral differential operators on C star, which is something like a lattice vertex algebra. But in terms of the actual associative algebra, this is saying that the universal enveloping algebra of SL2 embeds into, well, functions on the center of SL2 times some auxiliary differential. I'll come back to this in more detail in just a sec. But any other questions?
examples of what is a important orbit? How does the label
Yeah.
move? How does that-
Definitely.
Yeah,
Yeah.
and from this, it's impossible for me to judge the depth of this conjecture.
Yeah, yeah, of course. Yeah. So,
Also subscript on G or GSC.
the subscript here, it just says localized. So it's some micro-localization of differential operators on C.
That's C or
C to some
That's C to
power.
some
C to
numbers, so it's like Cn. Yeah, let me write C to the K.
Okay.
Some was to be right.
That's supposed to become G of C star, that example.
Yeah, or it's D localized on C.
Okay. Oh, it was never C star, it was like C2, remember? Or that.
Do you mean like here?
There's something in the right example.
In the right example? Yeah, so it's like a localization of differential operators on C, by which I mean differential operators in C star.
Oh.
Yeah. Okay, so to start with some preliminaries, to explain a little bit more about what each of these objects are. Let's start with talking about nilpotent orbits. So in type A, for any of the algebra, I'll write n, math cal n, inside dualism in the algebra to be the nil code. So this is the space of all nilpotent elements of the duolet. And in type A, i.e. in GLN, there's a nice correspondence which says that co-adjoint orbits in this nil code are in bijection with partitions of this n. And the way this works is that if I take some orbit here, I pass to its Jordan type. And moreover, this bijection is as a cosets. So partitions come with a natural dominance ordering, and that ordering is the same as the closure ordering on co-adjoint orbits. So if lambda is bigger than mu as partitions, then the orbit corresponding to lambda contains the orbit of mu in its closure.
Can you do an example for B equals 3?
Sure. Like you want me to write down the
The list of partition.
yeah. So for n is equal to 3, you have 3 partitions. You have going down from top to bottom. You have the trivial partition 1, 1, 1, which corresponds to the trivial orbit, just 0, trivial nilpotent orbit. You have 2, 1, which corresponds to the orbit of some element that looks like and then you have 3, 0, which corresponds to the entire node, which is the G orbit of Yeah, so the dimension of the orbits are, this guy has 0 dimensions. This guy has 4 dimensions, and this guy has 6 dimensions.
How do you see the dimension?
How do I see the what?
How do you see the dimension of the?
Well, I just know all of these dimensions by heart. That's my excuse. So, yeah. So this is the biggest principal orbit, so its dimension is equal to that of the nilpotent. And the dimension of the nilpotent is always dimension of G minus the rank.
Okay, great.
In GLN, it's dimension of G minus rank minus 1. That's, yeah. So that's like the trick. So, so these are some nilpotent orbits in type N, but what I actually want to define my W-algebras are not just these nilpotent orbits, but I want a certain kind of transversal slice to them. So, if I have one of these nilpotent orbits, and I have a representative in them, so I have some, if I have some chi inside, say, O mu, some nilpotent orbit, then it's true that O mu admits a transversal slice at chi. So i.e. there's some subvariety S mu inside.
And chi some special point on.
So this is true for any point inside of mu. So for any. Or at any. So there's some global slice such that the intersection of S mu with O mu is precisely chi, and this intersection is transversal. So there's no canonical way of constructing such a slice, mostly because if I conjugate chi by something that's an stabilizer, I'll get a different slice. So there's always some choices. But there's like a nice way of doing it, which is a construction of solidity. So if I'm given such a chi, then I can always associate an SL2 triple H, E, and F such that my element chi is equal to pair using the killing form with F. So I can always pick a H and an E such that this is true. There's some space of choices. I can always do this. And then S mu, so such a choice gives a grading to the entire Lie algebra. So G decomposes to some sum of graded components, Gi, under the adjoint action of this H. And the way I get my slice is I take chi plus the dual of the kernel of the adjoint action of E. So this gives you a pretty simple way of constructing a transversal slice at chi. You just look for the kernel of the adjoint action of E. And different choices of H and E will give you different slices, but they're all going to be valid transversal slices at that point. Let me write some this slice to the principal orbit is just some vector space, really. It's a three-dimensional complex vector space, and it's all the space that we introduced from this. Okay.
So S mu and mu intersect at the point.
Exactly, yeah. Oh. Sorry. Take the transpose of this matrix to align myself with the previous conventions. 1, 1, 0, S, X. Yeah, and so when SWJ is 0, this intersects exactly with that representative everyone. So far these spaces seem boring. They're literally just vector spaces, and they're always going to be vector spaces. But what's interesting about them is that they have an interesting Poisson structure. Interesting Poisson structure. And that's not super obvious in the way I've constructed these so far, which is just presenting them as a kernel of some linear map of a vector space. Does not make it very clear that they have any interesting Poisson structure.
What makes the Poisson structure?
So, I mean, it's an interesting Poisson structure because it's usually highly, it's very far away from being symplectic. So these things always have infinitely many symplectic leaves, and they provide like really interesting non-trivial Poisson structures on just vector spaces, and their quantizations using that Poisson structure is interesting. And to see that Poisson structure appearing, let me present the Hamiltonian construction of these slices, which relates to this talk more straightforwardly, which is by performing Hamiltonian reduction. So G dual is a Poisson variety. G dual is a Poisson variety under the KKS Poisson bracket. That's moreover, using that grading on G that I defined earlier from the top right there, I'm going to define n chi to be the space of all greater than 0 subalgebra of G. So G has some grading, and I'm just writing n chi for the subspace that's like strictly positively graded. And this thing is unipotent, and I'm going to define n chi, big N chi, to be its exponentiation unit. Okay, so that grading defines a unipotent subalgebra and a unipotent group. It's exponential. And moreover, there's like a natural map, literally just projection to a subspace, G dual to this n chi.
So just to sure understand, this Poisson structure, can that be determined by how it acts on linear functions? Just a linear function.
Yeah, absolutely. Yeah. So if I look at functions on G dual, then you can identify with that with symmetric, like polynomials in G, symmetric algebra on G W-algebra, and then the Poisson bracket is taken above theta. So yeah, so like I was saying, there's a natural map from G dual to n chi dual, which is, we call it phi. And this is a moment map. So, n pi moment map. And the claim that another definition of these transversal slices is that they are isomorphic as Poisson varieties to the Hamiltonian reduction of G dual using this moment map like chi.
So the positive half is determined by having an SL2 triple.
Exactly.
So how unique is that SL2 triple?
It's not unique.
So then choose a different one and then different G plus 0.
Yeah, so if you choose, so different choices of SL2 triples, like I said, will give you different concrete slices, but they're all isomorphic. They're all just going to be a vector space of some dimension.
Okay.
And moreover, they're always also all going to be isomorphic as Poisson varieties.
Okay.
So,
So was this a useful construction in the world?
yeah, so these slices and this kind of reduction is everywhere. This kind of like Whittaker reduction, as it's called. It appears all the time in a number of algebra contexts. One place it also appears everywhere in physics is this kind of Whittaker reduction is a very good model for what happens to the Higgs branch when you try and pick a certain kind of vacuum excitation value. So if you look at 4D physics or 3D physics, you can pick a certain nilpotent VEV
Big branch of what?
for 4D n equals 2 theory, or certain 3D equals 4, which theory is whenever you have a movement up to G dual, so whenever you have an action of G dual in this Higgs branch, whenever you have a W-algebra action of this Higgs branch, then you can always do this construction where you project down to a unipotent guy. You fix a VEV.
What am I constructing in Higgs branches with?
So you're like picking a VEV for the theory and floating down to the IR theory corresponding to that VEV. And then you're like giving a vacuum expectation value to the moment operator in Higgs branch.
And you want to know what?
What the
You want
resulting
vector
Higgs
theory that
Exactly.
at that point.
Exactly. After you've like flowed down all the way to the IR. And then the claim is that that's given by precisely this kind of reduction. Where I fix the moment map operator to have value chi.
So the n chi actions by conjugation.
Yeah, yeah, exactly. Just the conjugation action on G.
Be more explicit for that. What the map is for n equals 3.
N equals to 3. Yeah, so
The big fun map.
yeah. So for example, in the 2-1 case,
I mean, sorry, I'm not understanding. So if I pick some point on the Higgs branch, I bring some amount of gauge symmetry and whatever's left is okay. That's it. I expand around that. What's there?
yeah, so here I'm saying not that you just pick a point in the Higgs branch, but you give a particular vacuum expectation value to just the mode operator. So this is like picking the locus on the X branch, right? And then you're asking like, okay, so if I like fix that locus, what is like the resulting? What is the X branch of the resulting like theory in the infrared after I flew down? And the answer is like you can get that by performing this kind of reduction. You were asking me about an example. Let me do let me cop out and do the SL2 example.
Sure.
For SL2.
Yeah. For example, I want to know what is the big five with the model map.
Yeah, I mean, for SL2, this is going to be the only possible thing it's going to be, right? So if I pick my H, E, and F it to be what they normally are, E to be, and then F to be 1, 0, then my N chi is going to be the span B. And now the dual of it will contain pair with F. And this group is just going to be 1, 1, 0, U. And I claim that if you perform this reduction, SL2, where I start with SL2 dual at chi mod n chi, then I can identify the resulting space with space images these things. Okay. So to summarize, like I said before, all of these transversal slices are Poisson varieties, and one nice way of seeing where they are is by this construction of them using Hamiltonian reduction. And to get to what W-algebras are, so a finite, let's say, W-algebra is a localization of a transversal slice. So hence the convention at the very beginning, for every orbit, I have a transversal slice, and so I have a W mu in each nilpotent orbit, which is a quantization of the slice S mu. And what I mean by that is that W mu is some associative algebra, say over power series in some formal variable h bar, such that W mu mod h bar W mu can be identified with functions on S mu, and this identification is Poisson. Okay. And sorry,
When was this established? Like, how?
these W mu's are obtained as quantizations. I'm gonna be maybe not so good on my history for this.
I mean, were they first discovered independently and then the quantization result was established, or just quantized and said, aha, they're
quantizations is due to Losa, 2007, say, where he constructs these as quantizations very explicitly using the technology of measured algebra calculator. It's very quite algebraic. I think, for what it's worth, that the W-algebras in, say, physics, like as the vertex algebras, are much older, like 1990s. That's one interesting.
But the college was about homomorphic symplectic things, not about plus-one stuff, so.
Yeah, great point. So there's a trick. There's a trick that Losa used to construct these W-algebras where he uses a homomorphic symplectic variety, which has the W-algebra in there as a sub-algebra. That's the same trick that we're going to do. So what Losa did is he defines the so-called equivariant W-algebra, which is a quantization of the homomorphic symplectic variety G times this transversal stability slice. So it turns out that this thing is actually like homomorphic symplectic. And so there you can apply results of classical Palladian and show that there's only one quantization of this thing, speaking. And there's a subalgebra in here, which is just G invariance for this action of G on itself, basically. And that's going to be the W-algebra.
And the fact that you should get a finite W-algebra by this procedure, so again, this was expected from elsewhere, from before Lawson's work?
So
From physics, from math, from.
yeah, so
If you don't know, it's okay.
Yeah, my understanding is that it's my analogy with this, like how the VOA people define W-algebras. You take current algebra and you do this Grunfeld-Sokolov reduction. And if you kind of spell out if you look at that the right way, you can view this reduction by n as some kind of like analogous procedure of a DS reduction. Because it's basically like DS reduction is like you write some DRST charge for some stuff and you take homology. And similarly, when you take Gaussian by n, you can also write like DRST charge for that thing, take homology, and it looks kind of like it's almost like truncated zero modes, or same kind of format.
Yeah.
I think the more like physical way to think about it is that like this like Whittaker reduction thing is whatever wants to happen in Hanani-Witten diagrams when you have non-pole boundary conditions when a bunch of guys end on D5, and the reason why equivariant slowly slides is actually symplectic is just saying like if you have brain configuration where you have a bunch of D3s on one side, they all end on the same D5, on the other side they all get their own D5. That thing will tautologically, give you symplectic, homomorphic symplectic thing, and you just calculate what it is by standard stuff you can achieve.
Yeah.
But importantly, the slowly slice itself is not. Like it's only when you include G that it's actually.
Exactly. Yeah. Yeah. So, like I said, my understanding of it is that they first appeared in VOAs using Grunfeld-Sokolov reduction, and then this particular Hamiltonian reduction is a kind of like finite analog of that, and that I think was known sort of like pre-Losa's work, and Losa really showed that in the sense of Besser Palladian, you actually obtain W-algebras quantizations. And that's something that I'm going to use as well. So, and I'm not going to be talking really about vertex algebras because then this talk would go on forever. But what I do want to mention is that you can think of the affine W-algebras, which are vertex algebras. These are so-called chiral quantizations. ordering to partitions, and there's natural ordering to these transversal slices as well. So right here at the top, I'm going to put the W-algebra associated to the trivial partition, which is just the universal W-algebra of G. Then I can like flow down to say W2, 1 and these interesting things, which goes back into 1. So this is the sort of passage diagram for transversal slices. And what I want to say is that you can go down this diagram. So starting from this, you can get to one of these guys by performing Hamiltonian reduction. And moreover, in recent work by some authors, by Genra, Juillard, it's been noted that you can also do this sort of by steps. So you can also start with one of these like intermediate W-algebras, and then like further reduce to get one of these guys. So there are also like arrows going like this, which are also a kind of Hamiltonian reduction. With a different uniform group. And now the question is, can you go backwards? That's like the statement of inverse Hamiltonian reduction. So, are there maps going this way? So, to motivate why you think such a map might even exist, let me say a little bit of a digression about coproducts. So, from quite old work of, say, Brodel and Klesher, it's known that you can split apart these W-algebras in quite a nice way. So for example, if I have the partition 2, 2, this Young diagram looks like this, then I can split this Young diagram into 2 equal pieces, which are just 1, 1, and 1, 1. And now, the work of Butson and Klesher says that there exists a coproduct for W mu, which is 2, 2 here. And now this is a W algebra for GL4 to W mu1, which is a W algebra for GL2 times W2. So this has been known for a while. And inverse Hamiltonian reduction, this like map that goes in the other direction here, it's kind of like an example of this, but where you keep the Lie algebra on both sides the same. So, for example, going back to our GL3 cases, then if, say, mu1 was this 2, 1 partition, and mu2 is just this stack. W30 also GL3. But the difference compared to say here is that the remaining thing is like not a partition, right? Like if I take this and I subtract this off, I'm like not going to get a partition. This has a negative equivalence. And so the thing that I write down here is, well, it's a kind of shifted Yangian for this not quite partition minus 1, 1. And this is a so-called generalized coproduct that is all over the place, and many people in this group have many opinions and have been working on this. But I wanted to point out that this whole schema of inverse Hamiltonian reduction is an example of this more generalized coproduct between shifted Yangians.
Can you explain a little bit of what's the relationship between the two kind of coproduct? The first one is like,
I would say that they're like coming from the same like universal coproduct. So somehow all of these are instantiations of the coproduct on just the Yangian, and these are all various like quotients of that. So I take like various quotients of the Yangian, specialized to like interesting limits, and that universal coproduct in the Yangian should like restrict to these. And the fact that these are weird just comes from the fact that this is kind of a funny quotient. This shifted guy.
you say the last one is the truncated shifted left.
Yeah, it's a
Which
truncated
one?
It's y0 minus 1.
So this is a finite statement about finite algebras or affine.
This is a statement for finite W-algebras, but there's an analog of this for the affine Yangian, which would be the statement for the affine W-algebras.
Well, that's a W30 is the algebra.
So W30 is, yeah, it's just the center of Eugene. Yeah, it's a commutative algebra.
How big should I think of this as a y?
This y minus 1 something.
N-dimensional, finite-dimensional.
So it's finite dimensional. It's in this case, this is just going to be this guy is going to be just differential operators on C star.
What did you say was the center or something?
Sorry.
Can you repeat things as a
Yeah. So this guy W30 as an associative algebra is just isomorphic to the center of U of GL3.
And what is the superscript 0, 0?
These Yangians take in more parameters. So I've been suppressing these just so that we don't get into Yangian labeling combinatorics. But a Yangian has a shift and a truncation parameter, and they both describe a subquotient of the Yangian effectively. The two parameters are related to how you take that subquotient. I can explain more, but I don't think it's particularly related right now.
Are these a finite double algebra?
This is a finite double algebra.
Special case of the Yangian or how kind of a quotient subgroup?
Yeah. So to be very precise, there's a specialization of these finite W-algebras where you quotient out. They all have this like center, and you quotient out that center. And those are given by the Yangian, truncated shifted Yangian of n0 and then u, for whichever W-algebra.
Okay, only after your quotient on center.
Only have to quotient out the center. This is because, yes, this was true. If you wanted to recover the whole thing, then you have to use the deformation parameter. There are these Okay, so hopefully I've convinced you that this inverse Hamiltonian thing is an interesting thing to study, at least if you're interested in these general coproducts, but also if you're just more interested in the structure of the algebras in general. I would say a little bit about exactly how we're going to construct this algebra. So the strategy is,
And just so my understanding is we will have understood the conjecture as something that's proven, or we will have understood something before. I mean, somebody can make, or we will have understood something. Like, what is the give you?
yeah, so the conjecture is that like these maps exist,
Okay.
and we're going to prove that.
Why is it important?
Sorry?
Why is it important?
Yeah, so I mean, one reason is to do with these generalized coproducts, which I think are interesting in their own right. They're like really not well understood. They're not co-associative, for example. They have all these like, sort of weird pathological properties, but lots of things point to their existence, and this gives you one concrete example of them in cases. Another reason is that for the vertex algebras, something that VOA people are interested in is what these inverse Hamiltonian reduction maps have to say about the representation theory of vertex algebras. So you can start with like modules of the Versoro or W3, and you can produce modules of the current algebra or the Brzezinski-Kolb algebra using those. And that's done by using this.
So if you have that, then you can solve a mathematical problem.
Exactly, yeah. So it's like a really important tool, and it's being used to like study a lot of this representation theory like throughout in these like low rank examples where people just did this by hand. So being able to show this for general like type A just gives you a lot of power.
So which color of the arrow is the inverse Hamiltonian reduction? Purple?
Up.
Up.
Yeah. Hamiltonian reduction is moving down, inverse is moving up.
And why it gives you power because if you understood it between one of these guys, you understand all of them, or like what's the
Yeah,
power?
so the point is that like you're building up these representations in quite a nice way. Like this auxiliary algebra that you're tensoring on each time, it's like a very simple algebra. It's like a lattice algebra, or it's like a beating out system, whose representation theory is like well understood. And so the point is that you can start from like modules of like the Versoro or W3 and construct a bunch of modules in all these intermediate W-algebras, which are like a little less well known. But the ingredients that you're using to do that is like a simple thing each time.
So these generalized coproducts, like, they aren't like conjectures exist?
Yeah, there are examples of them. This is an example of them.
Like, when you construct these maps, like, do you know that they're like the generalized coproducts, or is it just like something that could be?
Yeah, so that's a good question. I would say that they agree with the map that's meant to be the generalized coproduct of spaces. So I understand the classical limit of this map very well, and in that case, it agrees with the classical limit of the generalized coproduct of spaces.
What do you basically?
Sorry, let me just say that the classical limit of that map, when I take h bar to 0, agrees with the classical limit of the generalized coproduct. Okay, so let me sketch, in my remaining time, let me sketch like how the proof of this works, because I think that's like the more interesting thing. So the interesting thing for me is that this is quite an algebraic statement, but I want to prove this using like a bunch of geometry. So minimal orbit going around here. And here is my point chi. And here is a slice of point chi. So this entire, all of this stuff, I'm going to call E1. And this transversal slice at chi, that's my estimate. Okay, this is like my rough Joy representation.
And you're using the fact that S is one of the, I mean, the number of non S is up.
Yes, yeah, same. Here, yeah, so the point is that I drew this really suggestively because it kind of looks like if I drag this slice around along this like orbit, this over here is OMU2, and it looks like I'm filling out an open, like a dense open in this like nilpotent.
So I can slow down a little bit. Where's the OMU1? Where's the OMU2?
So OMU1 is this point. And so its slice is like
Yeah.
forward. OMU2 is this like one-dimensional guy whose closure will contain OMU1.
Okay.
I'm trying to statistical control. I'm running out of dimensions here. And SMU2 is a slice to that orbit at some chi.
Great. Thank you.
And what I'm trying to say using this drawing is that if I like drag this SMU2 along this orbit, I'm going to like fill out SMU1.
Almost.
Almost a dense open inside it, right? So what I claim is that
Why not all
yeah, so one thing is that if I like drag this around to this point, it's gonna like intersect OMU1, which is like not, which in this picture it's not so bad because OMU1 is just a point. But if OMU1 was an interesting orbit, then it would mean that my slice is intersecting, that I'm gonna intersect the orbit too many times.
But you're never going to be able to drag the slice past through that point. Are you able to?
No, somehow you're gonna have to like jump. That's why this picture is like very suggestive.
Right. Can't simply chi to that point.
Yeah, exactly. Yeah, yeah. This picture suffers from not having enough dimensions. But what this cartoon is suggesting is that if we could construct something like SU2 times these auxiliary directions that I have to like pull this thing along, that's something like T star C, maybe some opens like that. Then this sits as an open inside SU1. And of course, every time I have an open inside some big affine variety, this implies a pullback of functions.
Sure, confused. Where does the T star C factor come from?
That's meant to represent these like auxiliary directions that I'm pulling across.
I thought that's a degree of freedom for chi.
They're just dimensions are different, so you have to, if you want to, right?
Yeah.
You want to have an open value.
Yeah, there are going to be some auxiliary factors, right? Like the point is that this SMU2, I'm going to need to like drag this guy around, but this picture seems to suggest that that's only like the value of chi. But unfortunately, this picture this restriction on functions, if I'm like able to somehow lift this up to the quantization, then that would give me my inverse Hamiltonian motion.
Do you have some geometry in mind that context that would be good for you?
So in the affine case, I'm gonna replace everything in sight with like loops. That's nice. But somehow this like special open set that I like really want, it's like really just a finite guy. I'm just taking like that and loops into that. I don't have to like do a new construction on a good setting. That's really the crux of how we were able to evaluate.
So does it mean that you found like for some subset of vertex algebras, someone knows how to think about them by this procedure?
Yeah, exactly. Yeah, we're like able to construct this like family of vertex algebras that are like a sheaf for this thing. And like you get these by like restricting just the sheaf.
And probably to put some of the really nice thoughts that it will work.
Exactly, yeah, exactly. So like what's important here is that like the geometry and the vertex algebras are nice and simple enough that we're able to do this. Exactly. This is my strategy for constructing this map. I'm just gonna like produce an open set and I'm gonna like quantize this map. So strategy. Is find open set such that for whenever u1 is less than 2, I have S of mu2 times T star of C to some power times T star C star includes into S of mu1 and obtain reduction by quote quantizing the restriction functions. So
So when you write T star C times T star C star, copy some of those.
Yeah, so I'm just looking ahead to what I know the answer is going to look like. So like I sort of suggested here, that there might be some points where I don't want to be able to like drag my guy through. So I'm not always just looking like T star C, I'm looking for some openings in T star C.
Okay.
And that precise open is like, or T star C is the multiplicity, and that opens will look like a bunch of T star C's, and then one T star C star. So there's only like one paper plane on how to go. So there's some there's some really nice, interesting things to say about how to construct this open set. Go Yeah, so it's because, like you pointed out at the very beginning, these spaces are not symplectic, and so to actually do something like best calculated, we need a whole symplectic version. And so we're actually working with these equivariant solidity slices that I mentioned. Those appear as so these equivariant solidity slices, G times S mu, these appear as Coulomb branches of curves that look like n minus 1, 1, and here you have n minus mu1, n minus mu1 minus mu2, well, oops, n minus mu1 minus mu2. So these all come from having some like Dirichlet boundary conditions on one end and some kind of non-equal. But importantly, all of these are only generalized slices in the Hamiltonian because they have no framing.
Sorry, question. What is mu1, mu2? Are they number or? Are they
Yeah, sorry. So mu here being like a mu.
So it's just only real. mu1.
Yeah, so I'm thinking of mu as a partition whose parts are like mu1, mu2, mu3, mu4.
Okay, so
small n.
partition of big n into.
Yeah, exactly,
So-
exactly.
Okay,
And then the step sizes are like given by the partition chunks.
got it.
Yeah, not to be confused with the mu1.
Yeah, yeah.
But the way we constructed these is by using simple multiplication map on generalized affine Hamiltonian slices. And we were able to show this result. So, there are that whenever mu1 minus mu2 looks like something minus 1, 0, 0, 1, whenever you have two partitions whose difference is just something like this, then there exists an inclusion S mu2 times T star to the C.
So this is like the longest root.
So it can be any root. Yeah, but just any negative root. So T star C to the length of that root. So T star includes into SQ1. So this is part of a more general result on affine Hamiltonian slices, which says that in general there's an inclusion for any co-weight GER mu2 times GER mu2 plus alpha minus alpha includes into plus alpha
And you guessed that this was the case by physics first, by ring pictures, or? Well, were you guys the first ones to write it down?
Yeah, so this was a suggestion of Joel Hamilton. our initial like attempt at this whole inverse Hamiltonian rejection was very much like trial and error, and he noticed that the answers that we were getting were examples of this specific multiplication map for the case where mu1 minus mu2 was just like minus 1, 1. And we used, and then that was like the sort of evidence that we were heading in the right direction, and that's what we used to and extended to this case. We just took a more general.
What's the multiplication map?
Right, so it's the map on, it's a map that takes it's this map that takes two quivers and just like adds them. It's the one that, example,
Multiply the estimations.
yeah, that one. So it would take something like n1, k1 times n2, k2, and embeds this inside n1 plus n2, k1 plus k2. So it takes the Coulomb branches of these two guys and embeds it into the Coulomb branch of this guy. And this here is a very special example where you split off an abelian gauge theory or just some abelian gauge theory with fundamentals.
The quiver that you erased, like, what if ends of like U1 and negative U1?
Yeah, so I split my mu into some parts, mu1 up to mu small m, and so.
Oh, it was like single mu.
Yeah. I'm just like subtracting off partial sums at the
So
vertex.
n minus mu1 and then n minus U1 minus mu2.
Exactly, yeah. I'm subtracting of like the partial sums in each node.
Just a question. So this slowly slice, are they also special examples for slice of Hamiltonian algebra branch?
Yeah, exactly, yeah. So, like I said earlier, you can recover these by taking the Hamiltonian slice for ger at mu and n times omega, the first fundamental coweight. But that's going to be the one where you, again, if you want to recover the full slice, you should take the family of this guy where it's like the full base. That becomes the whole thing.
But also originally you had some kind of product, not product.
Yeah, great. Yeah. So this is a product on spaces, and so it's a co-product on functions. So when I take functions, the arrow is going the other way. So I get like a map that splits functions on this guy into functions on this guy times functions on this guy. Yeah. So the point is that we're able to show that there is some nice geometry that does the first part of this. It produces some open set inside this transversal slice that looks like the smaller transversal slice times some auxiliary factors. And then now, like I said, I want to use just that geometry to like construct the map on like the quantizations. And that I'm going to use.
So basically still you're saying that understanding what happened in the finite case, it suffices to understand that finite case.
Yes.
So then you must have some very precise notion of what this high optimization means, right? That
Yes.
It's actual machine code.
Yes. Yeah. So we have a very precise.
Are you guys the first ones to have such a thing or do such a thing?
Yes, as far as I'm aware, yeah. We have a pretty, we have a very good understanding of something that's not quite as strong as like Westerkampendorf Canadian quantization, where you like literally are able to like identify the moduli space of quantizations. But we have something that in like some special cases is like approaching that. So we know exactly how big the moduli space of chiral quantizations is in some very specific
Why do
cases.
I care how big is the moduli space?
Yeah, great question. So the issue about being able to no, I think that's a great question. So the reason is that like when you just say that you have a map on like classical functions and you want to like lift it to a map from like their quantizations, that's like the wrong thing. You can't like lift things like that, right? So you have to like have some justification for why like things work out. And the way you can do it in finite type is you can appeal to like all these rigidity results. So in finite type, for example, just so 2. So we're able to construct some sheaf a mu on this linear slice test mu, whose restriction gives a quantization of small guy So I have some sheaf whose global sections is the W-algebra, the equivariant W-algebra. And I'm going to restrict it to this open set that I've defined using my like finite geometry. And I want to recover the smaller W-algebra. But to do that, I need to
What's that?
yeah, so is the strategy for how to like lift this map on functions to a map on the quantizations. And the way to do that is you construct some sheafy.
So first you have this open embedding, right?
Yeah,
Okay.
exactly. So first I need to construct some sheafy version of my quantization. So I need to construct some quantization that knows how to restrict to open sets. That's my AU. And then, just like with functions, my plan is to take this AU, this sheafy quantization, and restrict it to this open set. And then I want to justify that this thing is isomorphic to the smaller W-algebra times these auxiliary differential operator.
So what is the factor of big G doing here?
You can ignore it if you want right now.
Does that come from a theorem or is it?
It's coming from there, yeah.
So you have another version where big G.
Yeah.
It just doesn't do anything on big G or it varies over it.
It is equivariant with respect to that big G. So it's so the map is equivariant with respect to the action of G on itself. So you can take invariance. I want to be able to take my sheaf unrestricted on this open set and produce my quantization of SU2, like this guy. But I don't actually know that's true because I don't really have that much control over sheets or associative algebras. But what if one thing that I can say is that this AMU, when I restrict it to my open set, it's a quantization of that open set. And if I knew that that open set only had one quantization, then this isomorphism is always true. And that's why it helps to know the modulus space of quantizations. So if you know, for example, that the space of quantizations is rigid, show that this special open set that we describe, this SME2 times these like auxiliary directions, it has like a unique quantization, which I suppose. That's like the important part.
How do you spell that?
So luckily for us, in the finite case, this is old work. So in the finite case, this is work of Professor Kalidin and Lissa, going back to 2007. In the affine case, this is the new result. This is new work by us. So,
So you chose rigid or you chose like?
we show that it's rigid, so I'll write the most general result.
The question that how do you produce this kind of sheet in mu? Like how
Yeah.
are you able to show that on the sheet level restriction?
Yeah, exactly. Yeah. So there's some technical details about like localizing this sheaf that I left out, but the original construction of Kalidin, it's a sheaf. It produces a sheaf on this symplectic scheme whose global sections are a quantization, and you can restrict it to within sets to produce quantizations of that within set.
Yeah, but why that's not enough to? Are you saying you cannot?
You don't know which quantization it is, right? So
You're saying the intrinsic quantizing sheaf on the smaller guy compared with the one coming from restriction.
might be a different guy. Yeah, there might be a priori different
Yeah.
guys, right?
Okay.
Yeah, because the smaller guy might have different quantizations,
Okay.
right? And so that's the thing that you're worried about for this kind of like rigidity.
And sheep is a vector one.
Yeah, exactly, yeah. Okay, so I'll write down the,
For Coulomb wrenches and stuff, space of quantization is usually just masses or something like that.
yeah, that's right, it's
So
just
even,
H2.
even if you don't have a unique one, I mean, is it not? Don't you just try to match like, say where the masses go? I mean, it doesn't seem like the end of the world.
No, so the point is that in the finite case, there's a lot of things you can do. You can just track which quantization you're in by the fact that the theory of like Kalidin is like strong enough to be able to track like what happens to like the quantization as you restrict. Like you can say what happens to those masses, and you can conclude that you must be in like this particular quantization. The point is, however, in the affine case, this is like not bad. You don't have this kind of technology.
Yeah, so like do you still have enough of a statement that you can say like, because what I'm saying is basically instead of saying rigid, we can still say like to within finite dimensional ambiguity is still fine. Do you still have some like to within finite dimensional ambiguity in affine case, or are you like really only consider?
Yeah. So so for this particular example, the answer is that in the affine case, I'm able to show that things are rigid. It's like unique contour isomorphism. But the most general result is that like there's some like finite dimensional ambiguity. So let me.
But you ended up proving that.
Yeah, we ended up showing this by just like establishing that things are rigid. There's like no ambiguity. There's only one quantization. So
Even though there are ambiguities in finite.
Well, I think the point is there can be ambiguities, but if you kind of pick sort of small enough charts, then they're wrong. Because it's like,
In the charts, you don't see that.
yeah, well, because it's like the masses, like really those are like whatever periods of
Yeah.
eclectic form over some cycle. And the point is that like if you go to a locus where you actually don't have the full cycle in the chart, then like
Yeah.
you can't take periods. So you know, like if you just have like cotangent to CN, just a chart in anything, like that's always just
Yeah, right.
So like Spencer was saying, the ambiguity is given by the second drum homology and in the final case. And so if your spaces are just like vector spaces or vector spaces times C star, H2 is just vanishing and there's no ambiguity. And what we're able to show is that in the chiral setting, if you have some symplectic variety with Y such that its third de Rham cohomology is this is a technical assumption concentrated in a single graded degree.
what's the word?
Yeah, we're trying to be so for a action of system H bar Y that scales the symplectic form with weight so if Y is some symplectic variety with an action that scales its symplectic form with weight 1, then that extends to all of the de Rham forms. And in particular, if the third de Rham homology is concentrated in a single degree, this is always true for the cotangent bundle of anything, for example, but it's a technical assumption in other cases.
I thought any connector was gonna actually.
Sorry, it's not, I mean, it scales the symplectic form. It's not a symplectic organism.
You have cohomology with anything.
Yeah.
The group acting on anything. Then like the continuous group never acts any single cohomology.
I don't think that's true. You can definitely have like,
No, because you have this formula for lead derivative of like the anti-commutator of du and IB is Q trivial, so that means it's a big cohomology.
And is it H3?
H3, yeah. Yeah, so the claim is that,
And a single equivariant degree.
so, if you have this action on just Y that scales the symplectic form, it acts on all the de Rham forms, and in particular, it acts on the cohomology as well. And so it grades the cohomology, there's some like auxiliary gradient to it, and all I'm asking is that like the third de Rham cohomology is just in a single degree. It could be degree 0, degree 1, degree minus 1, that's just in some degree.
Oh.
I'm saying it's always going to be a degree 0.
I mean, for a homomorphic symplectic, I just 0. There is no study now.
There can be H3 for commonplace symplectic things. Definitely, yeah.
So degree means algebraic weight here. So does degree means algebraic weight here?
Yeah. The weight under that C star H bar.
Is 3 like special or something for like this to be true? You said it's true for like cotangent bundles?
Yeah. And I'm saying that like this fact that things are concentrated in a single gradient degree is true for cotangent bundles. Otherwise,
Would that be true for like all like de Rham homology degrees or just only?
I mean that's going to be true, I think, for all de Rham homology for the case of the cotangent bundle. Because there, the action of C star H bar just scales the cotangent by this 1, and so each de Rham form is going to have like weight equal to its de Rham. It's like a class. It's
Wait, but well, when you say it acts, you really mean it's coming from just pullback action on forms.
yeah.
Yeah, I'm pretty sure that's always just going to act trivial and normal.
It's the loop space of Y, so it maps from the formal disk into Y.
Punctured is or just
Just unpunctured.
unpunctured?
Unpunctured formal disk.
What is it called? Arc?
It's positive, yeah, from arc space. Yeah.
Is there an example that one can see this phenomenon?
Yeah, so the clearest example of this is for the case where Y is something like cotangent bundle of something. So when Y is a cotangent bundle of X, then this is a result that's been known for a while. This is a result
where X is.
where X is, say, smooth and affine. Then this has been known for a while, and it's the result for classification of so-called chiral differential operators. Where you see that if you restrict to a bunch of patches that just look like flat space, you just restrict to a bunch of T star C patches, then you get, there's only one kind of chiral differential operator in each of those, and then to glue them all together, you need to choose some class in H3 to glue them together. So you have some ambiguity given by H3 for R.
So what if X is like something not affine, P3 or something?
Yeah, so our result is really only for symplectic affine varieties.
I mean, I think most column branches have H3 0, right? Well, it's only the column branches of three-dimensional cases that's zero H3. You have to go to multiplicity things, which are not very clear.
Yeah, that's definitely true. I mean, you can consider things where you just have multiple C star factors.
Yeah.
That's like the rule that, exactly, yeah. And somehow this like ambiguity is related to how you ask those C star factors to talk to each other. No, sorry, there is actually an example which is important where you do have an H3, which is in the case of the equivalent that I wrote down before. This guy, the n minus 1, 1, and n minus e1, and so on, whose Coulomb branch is g times s mu. This has an interesting H3 because it has H3 Durand, which is H3 Durand G, which is interesting in one dimensional. So that's like the biggest example where you do have an interesting H3. You do have an interesting space of quantizations. Yeah. I think I'll end that on the results of organizations on the board.
Great.
All right, let's begin again. Questions? No question. So this quantization, how is this related to this Coulomb branch coproduct project?
That's a good question. So the Coulomb branch coproduct is it's about like the finite case of this,
Yeah.
where we're like very explicitly like describing that coproduct in a bunch of cases. This is kind of about this project is trying to get at the affine version of that.
You mean the chiral part?
The chiral path, exactly.
But the double part was related.
Yeah, exactly. Yeah, like the whole point of this approach is that we're using always just the finite geometry, but we're able to use some advances in understanding vertex algebras to be able to like lift like a result from finite geometry to prove something like vertex algebras, instead of having to deal with some like more crazy infinite type geometry or something like that.
Are you the first guys to do such an idea? I guess I asked this already, you said yeah.
Yeah, as far as I'm aware.
So you have a known asset in study.
Exactly. Yeah.
Okay.
Yeah. Like the point is to try and realize these vertex algebras as sheaves and use the same kind of techniques that people do for associative algebras and quantizations, but for vertex algebras.
Do you have some physics explanation why such a simple loop exists? Like, do you understand why this had to happen?
Yeah. So the physics model of what's going on, roughly speaking, it's like we're looking at like so these kinds of CDUs that appear, these are like the curved beta gamma systems on some target, say like Y. So we're sort of generalizing that here in this for where Y is just not of a cotangent to. So these like curved beta gamma systems, there's been like lots of studying done for them, and like different classes that you can have and how you glue them together, and all of them relied on the fact that Y was like globally a cotangent bundle. Here, like we're making the assumption that like we're like relaxing that assumption. So Y is like no longer a global cotangent bundle, and we're trying to like give a description of what is still the space of like gluing that you still have, but we're trying to approach it in a slightly different way.
But so aren't these VOAs that you get related to these corner VOA, junction VOA things that Coyote does? Or
Yeah, so a lot of these like W-algebras are corner VOAs, especially these like equivariant W-algebras. They're all corner VOAs.
But is it true universally that for like any chiral quantization with a full branch or something, that's going to be a
Corner VOA? That's an interesting question.
I mean, I feel like it just has to be just dualities moving the brain, like.
I think probably the answer is second. I think the answer is yes, in a lot of the things that you get. In fact, this was like part of what Dylan presented when he was here about vertex algebras from devices in Calvian threefolds. And like roughly speaking, all of those have like a nice geometric like limit.
But, well, I'm asking that because if you know something like that, if you have something stable like that, then it shouldn't be that hard to directly relate the kind of two appearances of coproduct. Because there's kind of two ways you can think about the coproducts and the affine Yankees. You can say they're either still, well, you can say they're still like well approximated in finite geometry, but